Thank you so much, Alison. And just, yeah, thank you to the entire Foresight team for making this happen. I'm going to set my timer because 7 minutes is quick. Okay, so hi, folks. I'm Jacques. I'm a program director at ARIA. If you haven't heard of ARIA, ARIA is a R&D funding agency with the express mission of pursuing research into areas that seem speculative, but if true, would really be transformational on a global scale. So I lead the Precision Neurotechnology program there, so all of the neurotech efforts at ARIA. It's pretty exciting to be here at this time now because I'm beginning to think about what else ARIA can do in the neurotechnology space. So what I'm going to share with you is just some ideas that I'm kind of obsessed with that I just can't stop thinking about, and I'd love to get some feedback and we can discuss that. Let's see if this guy works. Okay, great. So I conjecture that by virtue of us all being in this room today, we're united by the idea that neurotechnologies can radically improve the human condition, okay? Whether that is things like deep brain neuromodulation for a variety of intractable neurological and neuropsychiatric conditions. We're seeing incredible work in areas like treatment-resistant depression, chronic pain, epilepsy. There's just really amazing work there now. Or it's things like intracortical BCIs to be able to act as a motor or speech prosthesis for people with severe motor impairments. Or even cell and gene therapies. I actually think it's really important we include these as well. We're seeing amazing work in the cell and gene therapy space. Recently, just a gene therapy for Huntington's disease. Cell therapies, we're having people with Parkinson's that have been implanted with dopaminergic precursor cells that are autologous, and they're not even on immunosuppressants, okay? Really actually getting to the disease itself. Okay? And as a kind of footnote, I just really think we should think about the broad spectrum of biologics as well as hardware. And there's actually a ton of interesting white space at the intersection between them. So I would say, as the people in this room who are building these technologies, it is incumbent upon us to think, how do we actually get them to the people who need them the most? Okay? And I think we can look at a case study. Look at the case study of deep brain stimulation for Parkinson's disease. So if you plot the prevalence of Parkinson's disease, this is in the US, as a function of time, and also the number of procedures for DBS as a function of time, you'll notice two things. One, we're massively underpenetrated, okay? It depends who you speak with, what the eligibility criteria is, but we're at least an order of magnitude, potentially more off. And second, it's not even increasing at the rate that it needs to, okay? So I think the question for me is, why is this the case? And I would argue that this is the case for one of our most well-tested neurotechnologies. It's been FDA approved for a quarter of a century. It's well reimbursed. We can figure out if someone can respond to it. Emerging technologies for new conditions where you want to do all of these incredible things, you're going to face this exact same issue. So we need to take this scaling, if you want human data, incredibly seriously. So I think there are two buckets why these technologies don't scale. The first is on the efficacy side. For many of these disorders, deep brain stimulation doesn't actually treat the disease itself, it treats the symptoms, okay, motor symptoms. And actually for many neurological and neuropsychiatric conditions, most of our interventions aren't working at the same level as the disease itself, at the circuit level. So this was actually a big motivation for our first program, the Precision Neurotechnology program. We're actually putting $90 million towards building much better circuit-level neurotechnologies. And the second part is on the procedural burden. I actually had the privilege of watching a number of DBS procedures be done the other day, and be under no illusion, implanting something intercortically into someone is a very serious procedure, okay? There are single-digit likelihoods, risks of infection, intracerebral hemorrhage, that gives rise to patient-clinician hesitancy. And if you just think about the kind of workforce question, there's only so many places you can do this. In the US, there's probably only a few hundred for functional neurosurgeons. Building new operating theaters is just incredibly expensive. So, I'm at the Foresight Institute. Why have I been rabbiting on about a 25-year-old technology? Okay. My point here is that any emerging technology doing all of these things must radically reduce the procedural burden. Otherwise, it's always going to be stuck in a kind of high cost, low volume, last resort procedure. Okay. And this is why I'm here, I believe there are technological solutions which mean that we can solve this now, which we couldn't just a few years ago. So, what would our wish list be for a kind of next generation scalable neurotechnologies? First, we want it to be delivered in a way that doesn't require transcranial brain surgery. Can it be delivered systemically through the vasculature, through the CSF, potentially even through direct neural routes? We want it to be able to write activity in a wireless way. We want it to be able to either based on exogenous signals from a kind of from a controller or endogenous signals based on neural activity. And finally, we want it to be able to report time series data from a targeted brain region. So we're not integrating across the entire brain, but really getting out from a single localized region. Now, the neat part about my job is that I don't have to come up with the solutions. I can just put forward problems and then smart people like you can come up with all the solutions. But I'm just going to share in the last minute some things that I think are really inspiring and which might provide possible solutions. On the systemic delivery, I think there's huge opportunities in actually leveraging biology to help us get things into the body. You know, this is an example of an immune cell. There are certain immune cells that endogenously cross through the blood-brain barrier and target regions of pathology. There's a whole field of loading them with things like PDMS kind of drug carriers. What else can we do? Beautiful work which has combined magnetic nanoparticles with AAVs. So you get the tropism of the AAV potentially crossing through the blood-brain barrier with the controllability of the magnetic nanoparticles. Finally, what other ways can we get to the brain? This is beautiful work from Jacob Robinson, Peter Kahn, who show that you can go in through the cerebrospinal fluid and actually access the ventricular deep brain structures and put a bioelectronic device there. What are other access routes that we haven't even considered? On the wireless writing, there's really exciting work in new biophysics at the moment. Can we leverage magnetogenetics? Certain fluorescent proteins have very strong magnetic responses. Combine that with bioluminescence, combine that with optogenetics, potentially you could have wireless control of deep brain structures. If we've got engineered cells within the brain, can we design new receptors that can sense neurotransmitters and based on that actually go and release new types of proteins or drugs? And finally, on the reporting side, can we use new techniques that actually allow us to read out gene expression in the brain? This is beautiful work from Jerzy Soblowski with these released markers of activity. So I'm at my time now. In our discussion, we're going to talk about what are new technological frontiers that will enable massively scalable paradigms for neurotechnology. So looking forward to discussing that. Thank you.
Thanks. Well, it's time for a question. Maybe shout it out to avoid feedback. Yeah, nice.
I'd be curious what you see are the primary medical conditions that you would encourage me to focus on. Because it's just like a vast, right? And there's probably things that are easier, like Parkinson's, and like things that are really, really hard. I don't know, certain types of strokes that are very deep in the brain. Curious whether you have opinions on
Yeah, well, I think my take is that if you're building like very, very complex technologies, you want to at least choose a indication of brain region where you've got some signal that it could be useful, right? Like I think about engineering risk and neuroscience risk. Like I'm more comfortable with engineering risk. So let's think about, there's amazing work in treatment-resistant depression at the moment. If you can modulate the subclassal cingulate for very, very severe people, potentially you could actually have very long-lasting effects. So I think that's a really interesting area. Parkinson's with dopaminergic neurons. There's a whole spectrum of things, but I'd urge you to really look into the literature and see where there is, a verified signal.
Oh yeah, okay. A quick
So very exciting. So massively scalable could mean several things. Could be massive connectivity, millions of neurons in a single brain. Could also mean everyone in the world can have one of these technologies, right? Massively scalable as far as you can get. Billions of people that use, it only has 100 or so electrodes, right? Mm-hmm. Yeah. So are you interested in both or?
Great question. I'm actually interested in how we can actually get these to people. I think that's really where there's just a huge white space at the moment. Like, there just aren't that many neurosurgical clinics. There aren't that many neurointerventional clinics. Like, what is required to have procedures that can be done in an outpatient setting? So I think the burden of brain disorder is just so huge. We need to look at ways of getting these to people. Flip.
That's a great question, and mine's a little bit related, which is, are you looking for technologies that can do all three of these things, or is doing one of them good enough if you can show that there's a path to getting to it?
That's a great question. I would say, like, I'm interested in all three, but really interested in this delivery aspect. How do we actually get things to the brain? Are there new ways to do it? So it's a kind of combination of like the intersection of delivery and performance. Thank you. Okay, we'll do more of this.
Thanks
so
so
much.
much. All right.